ADF7021 high-performance narrowband ISM transceivers. Welcome to the training module on ADF7021 high-performance narrowband ISM transceiver. This training module introduces the ADF7021 ISM transceiver, its features, and internal operations. The term short-range device is intended to cover radio transmitters which provide either unidirectional or bidirectional communication and which have a low capability of causing interference to other radio equipment. For designing an SRD wireless system, careful consideration needs to be paid to the choice of frequency on which your radio will be communicating over. For designers who are hoping to build systems which can operate worldwide, the obvious choice has been 2.4 GHz. However, for systems which require both range and low power, the sub-1 GHz bands, including other unlicensed bands below 1 GHz, remain compelling due to reduced coexistence issues and greater transmission range, both of which impact on power consumption, an important consideration in battery-powered applications. Many of the worldwide regulations governing SRDs stipulate narrow communication channels, which significantly limits the transmit bandwidth to less than 25 kHz or less, and thus the maximum data throughput. A narrowband channel is generally defined as a channel bandwidth equal to 25 kHz. Such narrow channelizations are needed in many cases due to a lack of bandwidth, and so there is a need to fit as many channels into a given bandwidth as possible. Due to narrowband nature of the channels, there are various difficult specifications to meet for both transmit and receive. In this training, we will list some of these specifications. The ADF7021 is the available solution that covers all of the various sub-1 GHz worldwide narrowband operating frequencies. It is a low-power, highly integrated 2FSK, 3FSK, or 4FSK transceiver designed for operation in the narrowband license-free ISM bands and licensed bands in the frequency ranges of 80 to 650 MHz and 862 to 940 MHz. It has both Gaussian and raised cosine data filtering options to improve spectral efficiency for narrowband applications. It is suitable for circuit applications targeted at European ETSI, EN300 and 220, the Japanese ARIB T67, the Chinese short-range device regulations, and the North American FCC Part 15, Part 90, and Part 95 regulatory standards. The ADF7021 supports a wide variety of programmable features, including RX linearity, sensitivity, and IF bandwidth, allowing the user to trade off receiver sensitivity and selectability against current consumption depending on the application. A detailed block diagram of the ADF7021 is shown. The transmit section contains dual voltage controlled oscillators and a low noise fractional NPLL with output resolution of less than 1 ppm. The VCO operates at twice the fundamental frequency to reduce spurious emissions and frequency pooling problems. The transceiver RF frequency, channel spacing, and modulation are programmable using a simple 3-wire interface. The ADF7021 also features a low IF receiver. The received RF signal is amplified by the low noise amplifier and down converted in quadrature I and Q to the intermediate frequency. At IF, the IQ signal is complex filtered and amplified. The receiver also features a patent-pending automatic frequency control loop with a programmable pull-in range that allows the PLL to track out the frequency error in the incoming signal. This figure shows the structure of the RF front end. The low noise amplifier, or LNA, features a differential input which enables to achieve a high level of resilience against spurious reception. The LNA is followed by a quadrature down conversion mixer, which converts the RF signal to the IF frequency of 100 kHz. The IF signal is further filtered by the IF filter, which is a fifth-order Butterworth polyphase filter. The LNA has two basic operating modes, high-gain low-noise mode and low-gain low-power mode. To switch between these two modes, use the LNA mode bit. The mixer is also configurable between a low current and an enhanced linearity mode using the mixer linearity bit. The quadrature outputs of the IF filter are first limited and then fed either the correlated FSK demodulator or the linear FSK demodulator. The correlator demodulator is used to demodulate 2FSK, 3FSK, and 4FSK. The linear demodulator is used for frequency measurement and is enabled when the AFC loop is active. The linear demodulator can also be used to demodulate 2FSK. Following the demodulator, a digital post-demodulator filter removes excess noise from the demodulator signal output. Threshold or slicer detection is used for data recovery of 2FSK and 4FSK. Data recovery of 3FSK can be implemented using either threshold detection or VDB detection. The clock and data recovery module in the ADF7021 device is implemented using an oversampled digital phase locked loop, operating at 32 times the transmit data rate. The CDR PLL synchronizes the received bit stream to a local bit clock, RX clock. The maximum data or symbol rate tolerance of the CDR PLL is determined by the number of zero-crossing symbol transitions in the transmitted packet. The CDR PLL is designed for fast acquisition of the recovered symbols during preamble and typically achieves bit synchronization within 5 symbol transitions of preamble. The ADF7021 also supports a real-time AFC loop that is used to remove frequency errors due to mismatches between the transmit and receive crystal or TCXOs. The AFC loop uses the linear frequency discriminator block to estimate frequency errors. The linear FSK discriminator output is filtered and averaged to remove the FSK frequency modulation using a combined averaging filter and envelope detector. In receive mode, the output of the envelope detector provides an estimate of the averaging IF frequency. Two methods of AFC supported on the ADF7021 are external and internal. Depending on the application, users can design a matching network for the power amplifier to exhibit optimum efficiency at the desired radiated output level for a wide range of antennas, such as loop or monopole antennas. The power amplifier is based on a single-ended, controlled current, open drain amplifier that has been designed to deliver up to 13 dBm into a 50 ohm load at a maximum frequency of 950 MHz. The PA is equipped with overvoltage protection, which makes it robust in severe mismatch conditions. The PA output current and consequently the output power are programmable over a wide range. The PA configuration is shown below. The ADF7021 supports 2FSK, 3FSK, and 4FSK modulation. The implementation of these modulating schemes is shown. In all modulation modes except oversampled 2FSK mode, an accurate clock is provided on the TX-RX clock pin to latch the data from the microcontroller into the transmit section at the required data rate. In all modulation modes, the deviation from the center frequency is set using the TX frequency deviation bits. The ADF7021 exhibits optimum performance in terms of sensitivity, transmit power, and current consumption only if its RF input and output ports are properly matched to the antenna impedance. For cost-sensitive applications, The ADF7021 is equipped with an internal RX or TX switch that facilitates the use of a simple combined passive PA or LNA matching network, which is shown on the left figure. However, the performance of this matching is degraded from 1 dB to 2 dB. Alternatively, an external RX-TX switch can be used, which uses a slightly improved receiver sensitivity and lower transmitter power consumption. This method is more flexible and less difficult to design than the configuration using the internal RX-TX switch. The serial interface allows the user to program the 16 or 32-bit registers using a 3-wire interface. It consists of a level shifter, 32-bit shift register, and 16 latches. Signals should be CMOS compatible. The serial interface is powered by the regulator and therefore is inactive when CE is low. Data is clocked into the register, most significant bit first, on the rising edge of each clock. Data is transferred to one of 16 latches on the rising edge of SLE. The destination latch is determined by the value of the 4 control bits, C4 to C1. These are the bottom 4 least significant bits, DB3 to DB0, as shown in the diagram. Data can also be read back on the S-read pin. The standard transmit or receive signal and the configuration interface to a microcontroller is shown. In transmit mode, the ADF7021 provides the data clock on the TX-RX clock pin, and the TX-RX data pin is used as the data input. The transmit data is clocked into the ADF7021 on the rising edge of TX-RX clock. In received mode, the ADF7021 provides the synchronized data clock on the TX-RX clock pin. The received data is available on the TX-RX data pin. The rising edge of TX-RX clock should be used to clock the received data into the microcontroller. The UART should only be used with oversampled 2FSK.